Let's see how quickly we can cover everything you need to know for AQA GCSE Physics Paper 1. This is good for higher and foundation tier, double combined trilogy and triple or separate physics. That's topics 1 to 4, that's energy, electricity, particles and atomic structure, but I like to call it nuclear physics. I'll tell you when something is just for triple, but not when something's just for higher tier, because to be honest, there's not a lot of difference at all. We're going to be belting it here, so pause the video if you need a bit more time to get your head around something you see. Let's go. Energy isn't something you can hold in your hand. It's just an idea. It's a number that tells us what will happen when objects interact in what we call a system. Total energy in any interaction is always conserved. Energy cannot be created or destroyed. Now, there is a small caveat with that, as energy can be turned into matter, mass, but it's still technically true. The whole mass to energy thing is only important for triple people in topic 4 when it comes to nuclear fission and fusion. There are what some people call different stores of energy. Normal people just say types of energy, but these days the exam boards are obsessed with the word stores, so that's what we're going to have to use. The energy in these energy stores changes when objects interact. Energy is measured in joules. An object can have energy in the following stores. Kinetic energy. We calculate it with E equals half mv squared, half times mass in kilograms times speed or velocity squared. The faster an object goes, the more kinetic energy it has. Gravitational potential energy, or GP for short, we calculate that by E equals mgh. That's mass times gravitational field strength, either 10 or 9.8 newtons per kilogram. You'll be given it in any question that involves it, times by height in meters. Technically, this only gives you a change in GPE, as the h here should really be change in height. The higher off the ground an object is, the more GPE it has, or rather, the more GPE it has available to lose if it falls to the ground. Elastic potential energy is what we find in, say, a spring. This is given by E equals half Ke squared. That's half times the spring constant in newtons per meter, sometimes called stiffness, times extension in meters squared. That's how much further the spring has stretched from its original length. Thermal energy, or change in thermal energy, is calculated with the SHC equation. Energy equals mass times SHC times temperature change in degrees Celsius. In simple form, that's E equals mc delta T. That delta or triangle just means change in. That's change in temperature here. SHC is short for specific heat capacity. This tells you how much energy is needed to raise 1 kilogram of a substance by 1 degree Celsius. It's different for every material out there. Remember that an increase in thermal energy results in particles moving faster, so this is essentially a way of measuring the kinetic energy gained by particles in a substance. More on this in the particles topic. We don't really talk about sound or vibrational energy, as this is just particles moving, so in reality it's kinetic again. Chemical potential energy, say in food or fuels, there's no equation for that, and that's more chemistry's remit, but you might have to mention at some point that these two things do have a store of chemical potential energy. In order for anything to happen in a system, energy must be transferred from one object to another or one store to another store. In a closed system, no energy is lost to the surroundings, no energy in from the surroundings either, which allows us to equate two lots of energy. That just means saying that two lots of energy are the same. For example, a roller coaster car teetering at the top of a ride just has GPE, gravitational potential energy, basically zero kinetic energy. As it starts to roll down, GPE is turned into Ke. Okay, I should probably say that its GPE store is decreasing while its Ke store is increasing instead. But all that really matters is that at the bottom, it's lost that GPE using this height here. So we can say GPE lost equals Ke gained. GPE equals Ke. So if it had this many joules of GPE at the top, it must have the same number of joules of Ke at the bottom. We can then rearrange the Ke equation to find its speed. For example, I always recommend rearranging equations using symbols, not words. So here I want to make v the subject, leave it by itself. So to move something from one side of an equation to the other, we just do the opposite with it. To get rid of the half, we double the other side. Then to get rid of the mass from the right hand side, well, we're multiplying by it on the right, so we just divide by it on the left. Finally, to get rid of the square on the v, we square root the other side. So speed v is equal to 2 times the kinetic energy divided by the mass, all square rooted. Then just pop in your numbers, punch it into your calculator, and boom, you got your answer. You could also equate elastic potential energy and kinetic energy, say if a toy car is pulled back on a spring and let go. There is a shortcut with the whole GPE to KE scenario, by the way. If we just equate the two equations, you'll notice that mass m is on both sides, so they actually cancel out. So rearranging this, we find that v is equal to the square root of 2gh. So really, we only need to know the height from which something falls in order to know its speed at the bottom. If you have to rearrange the GPE equation, just remember that the two things you have to move from the right-hand side have to go on the bottom of the left-hand side, multiplied together in brackets. You could get a situation where, for example, the roller coaster has more GPE at the top than KE at the bottom. Where's the rest of the energy gone, you might ask? Well, it must have been lost to the surroundings, so that means it cannot be a closed system. This could be due to work done against air resistance or friction. Work is just another word for energy used, by the way. This really does belong in the particles topic, but for some reason it's here, so we're going to cover it now. It's the specific heat capacity practical. We can find the specific heat capacity of a material by heating it up and measuring the change in its temperature. For example, we can use an electric heater that slots into cylinders made of different metals. We turn the heater on, use a voltmeter to measure the PD and ammeter to measure the current, and we multiply these to get power. More on this later, by the way. We use a balance to measure the mass of the block, and we use a timer and a thermometer to measure how much the temperature of the block has increased by in a certain time, say 60 seconds. We take the power and we multiply it by the time to get the energy that's gone into the block, and then we pop these numbers into our rearranged SHC equation. The issue is that while heating, some energy will be transferred to the surroundings, which means that the temperature change that we measure will be less than what it should be. So invariably, our final value for the SHC will be higher than the true value. Power is just the rate of energy transferred. Any rate is a change in something divided by time. Here's the equation. P equals E divided by T. The unit for power is W for watts, but this is just the same as joules per second. So my laptop has a 200 watt power supply, which just means that it uses 200 joules of energy every second. To find out how much energy it uses in a minute, we just rearrange this equation so E is equal to P times T. This is how you'll see it in your formula sheet, by the way. Efficiency is a measure of how much energy going into a system is used usefully. It's just a ratio or a fraction. So we calculate it by doing the bit divided by the lot. So in this case, it's the useful energy out divided by the total energy in. It also works with power too. Let's say that my power supply only supplies 120 watts of useful power to the laptop, even though it uses 200. So its efficiency is 120 divided by 200, which is 0.6 as a decimal. Multiply that by 100 to turn it into a percentage, and that means that it's 60% efficient. You could be asked to give efficiency as a decimal or a percentage. That means that 40% of the power or energy in is wasted. This is usually as heat lost to the surroundings, as per usual. If houses or other buildings don't have sufficient insulation, a lot of heat can be lost through walls, windows, doors, and the roof, etc. Just for triple real quick, we can do a practical on this by wrapping up cans with different insulating materials or different thicknesses of the same material, pouring in hot water from a kettle and measuring the temperature after a certain amount of time. The higher the temperature is at the end, the better the insulation. Energy sources are not the same as energy stores. Rather, energy sources are where we harness energy from in the world around us. Finite or non-renewable sources include fossil fuels like coal, oil and gas, all burned to create heat, for example in electrical power stations. Finite means that once used up, no more can be obtained. Nuclear fuel like uranium is also finite, although would not run out for a very long time. Renewable sources include wind power, hydroelectric power stations. Both of these are used to turn generators to generate electricity. Solar panels convert light energy into electricity directly. Geothermal power stations involve water being pumped deep underground to be heated. And biofuel is the term for any biological matter that's burned to produce energy. Electricity is one of those topics that people find confusing, so let's try and demystify it, shall we? Electricity is the flow of charge or charges, like electrons. They carry energy from a source of energy to a component, where the energy is released as another type of energy. Here's a simple circuit. We have a cell here. This is the symbol for that. This is the symbol for a battery. That's just several cells connected in line. We draw straight lines for the wires, which in this case are going to a lamp, a light bulb, and that lights up. Of course, you have to have complete loops of components and wires in order for these charges to flow. By the way, you're going to see me mix up cells and batteries in this video because they're just the same thing really, and they do the same job. Leave an angry comment below if you're really that mad about it. So what's going on here in this circuit then? The battery has a store of chemical potential energy. When connected in a complete circuit, this energy is transferred to the electrons, which move through the wires. This movement of charge is called a current, and we say it always goes from the positive terminal of the battery to the negative. Don't think about it too much. As the electrons pass through the bulb, their energy is converted into light, and some heat too probably, as they're never 100% efficient. This light and heat is then transferred to the surroundings, including your eyes, so you can see it. But the electrons don't just disappear once they transfer all of the energy to the bulb. As this is one big loop, these electrons are pushed back round to the battery by the ones behind them, where they're refilled with energy ready for another trip around the circuit. This constant flow of electrons transferring energy is what keeps the light bulb on. Because electrons are so small and there are so darn many of them, we don't deal with individual electrons, but instead deal in coulombs of electrons, or coulombs of charge. Similar to moles in chemistry, it's just a specific number, but we don't care what the number in a coulomb is. Potential difference, PD for short, also known as voltage, but AQA don't like voltage, tells us how much energy is transferred per coulomb of electrons. So if a cell or battery says it's 1 volt, that means that 1 joule of energy is given to every coulomb of electrons that pass through it. If a battery is 6 volts, that means 6 joules is supplied per coulomb instead. We measure PD with a voltmeter. Voltmeters always get added last to a circuit, as they're always connected in parallel to the component you want to measure the voltage of. In the real world, that means the leads or cables from the voltmeter always piggyback into other leads. If we put the voltmeter across the battery, it should measure 6 volts, right? Because 6 volts is supplied to the electrons in the circuit. That's just 6 joules per coulomb. But put it across the bulb and it should still say 6 volts. Why? Because the electrons have to lose all of that 6 volts worth of energy as they pass through. Okay, it might be minus 6 volts, but we don't care about minuses really when it comes to PD. We only care about the number. Here's the equation for PD. PD in volts is equal to energy in joules divided by charge in coulombs. In simple form, V is equal to E over or divided by Q. Q is the symbol for charge, but it's measured in C in coulombs. You'll see the rearranged version, E equals QV, on your formula sheet. Current, on the other hand, tells us what the rate of flow of charge is, essentially how fast is charge flowing through a circuit or a component. Like any equation for a rate, as per usual, it's something divided by time. So here, it's current in amps equals charge in coulombs divided by time in seconds, or I equals Q divided by T. Yes, we use capital I as the symbol for current, not C. Blame the French for that, as they called current intensité du courant. It does mean, though, that we don't get confused between current and coulombs, though, so we stick with it. You're going to see the rearranged version of this equation on your formula sheet. Q equals IT. That's I times T. We measure current with an ammeter. Note that it's not amp meter. Unlike a voltmeter, it must go in series. That means in line with the component we want to measure the current for. Components in a circuit have resistance, that is, they resist the flow of charge or current through them. But that's not a bad thing. This has to happen in order for them to work. A bulb has resistance, which causes energy to be transferred and light to be emitted. A resistor, of course, has resistance too, but it just produces heat when current flows through it. If we make a circuit with a resistor and change the PD available to it, what we find is that an increasing PD results in a greater current flowing. In fact, doubling one doubles the other, so we can say that PD and current, or V and I, are directly proportional. Drawing a graph of these two makes a straight line, and if we turn the battery round, we can get negative values for both too, but still a straight line through the origin. This straight line, a constant gradient, shows that a resistor has constant resistance. We say it's ohmic. The steeper the gradient of this line, the lower the resistance of the resistor, as more current is flowing per volt. The equation for resistance is Ohm's law. V equals IR. That's PD in volts equals current in amps times resistance in ohms. That's the unit for resistance. We can get the resistance of a component from an IV graph like this by just picking a point on the line and rearranging Ohm's law. So R is equal to V over I. For a resistor, you'll end up with the same answer no matter what point you pick. If you repeat the same experiment for a bulb in place of the resistor, however, you'll end up with a curved graph like this. This shows that the resistance is changing, the resistance of the metal filament in the bulb. In fact, you'll find that any metal has a changing resistance if you increase the PD and current. They're non-ohmic. At higher PDs, the current increases less and less, so that means they can't be proportional. This shows that the resistance of the metal is increasing with a higher PD and higher current. The change in gradient shows us that this is true, but we still just take a point on the line and use Ohm's law if we want to find the resistance. It's just that it does matter where you pick that point in this case. So why does resistance change for a metal? Well, it's because metals consist of a lattice or grid of ions surrounded by a sea of delocalized electrons. That just means they're free to move. Or rather, they're fairly free to move because they do collide with the ions as they flow. That's why the metal heats up when you pass a current through it. The higher the current, the more frequent these collisions are, and this makes the ions vibrate more and more, which in turn makes it harder for the electrons to flow. The resistance has increased. Now, as an aside, AQA have royally messed up lately in their exams, whereby they've asked the question, what would happen to a resistor if the temperature increased? To which the mark scheme says that its resistance would increase. It would act like a metal. They are wrong. Resistors are specially made from specific materials such that their resistance stays constant even if the temperature changes. If that wasn't the case, we wouldn't get this straight line for a resistor, and we might as well just use metals instead. Silly AQA. Now, there is another component called a diode. It will give you this graph. The circuit symbol might give you a clue as to why this is. A diode only lets current flow through in one direction. We say that in one direction the resistance is very high and it's very low in the other, which is why the current increases suddenly at around 1 volt. An LED is a light emitting diode. Similar symbol, just with a couple of extra bits. These are what most lights in electronics are these days, rather than filament lamps. They act in the same way as a diode, so they give you the same graph, but they just happen to emit light as well. We can do another practical on resistance by measuring V and I for a length of metal wire connected to a circuit with crocodile clips to calculate resistance of the wire using Ohm's law. Then we can move one clip further up the wire to see how the length of this wire affects resistance. You should end up with a straight line through the origin, showing that resistance and length of wire are directly proportional. Series and parallel circuits. This is where things get a bit tricky. Remembering what happens to current PD and resistance when we have components in series or in parallel. Here's the simplest series circuit we can make really, just two resistors in line with the battery. What you need to remember is that for components in series, total PD is shared between them, current is the same for all of them, and the total resistance is just the sum of all resistances. That just means add it up. Let's deal with that first point. If these resistors are the same, let's say 10 ohms each, then that 6 volts total PD from the battery must be shared between them. So if we put a voltmeter across each of these, they'd both read 3 volts. It wouldn't matter what resistance these resistors are. They could be 1,000,000 ohms each. If they're the same, then that total PD is shared equally. By the time the electrons leave the second resistor, they have to have lost all 6 volts worth of energy, ready to go back to the battery to be refilled. By the way, we can also call this setup a potential divider circuit, as the total potential, total PD, is being shared. If the resistors don't have the same resistance, then we can use the second point to help us, that is, the current is the same for both. Let's say the first resistor is 20 ohms, using 4 volts of the total 6 volts available. We know 2 things out of V, I and R, so let's use Ohm's law to find out the third for it, current in this case, I. Rearranging Ohm's law, we get I is equal to V over R, so that's 4 divided by 20, 0.2 amps. Same for the second resistor too. Is there also a second thing we know about the other resistor? Why, yes, there is. Remembering the first rule up here, we know that if the first resistor is using 4 volts of the total 6 volts available, well, then the other resistor must be using up 2 volts. We could then use Ohm's law again to find its resistance, 10 ohms. The rule of thumb is this. The greater the resistance, the greater the share of the total PD it gets. We can also use Ohm's law for a whole circuit. We just need to make sure that we're dealing with the total PD, total current, and total resistance. The rules for parallel circuits are the opposite. The PD is the same for every branch, current is shared between each branch, and the more resistors you add in parallel, the lower the total resistance. This, by the way, is because you're giving the current more routes to move through the circuit, which means more current can flow. So if these two resistors are connected to the 6 volt battery in parallel, you know straight away that the PD for both has to be 6 volts. Voltage isn't shared in parallel circuits. If, however, we say 0.5 amps total current is flowing through the battery and 0.2 amps of that is flowing through the top resistor, that must mean that there's 0.3 amps flowing through the bottom resistor. If you're not in a rush, why not pause the video and see if you can calculate these two resistances. By the way, if you want a little bit more help on this, then have a look at my video, How to Answer Any Electricity Question. It's not only metals that can change resistance. We can have a thermistor, and you have a circuit that responds to changes in temperature. A thermistor's resistance decreases if the temperature increases. So in essence, it does the opposite to a metal. In this case, if the temperature increased, the resistance of the thermistor would go down, as does its share of the total PD. That means the PD measured by this voltmeter will increase. This could be the basis of a temperature sensor for your central heating, for example. An LDR is a light-dependent resistor, very similar to a thermistor, but resistance goes down with increased light intensity, not temperature. So this circuit could be on the top of a street lamp. Light intensity goes down, resistance of the LDR goes up, as does its share of the voltage. This could then be connected in some way to the light bulb, so it turns on as it gets dark. We know from earlier that power is the rate of energy transferred, so energy divided by time. However, when it comes to electricity, we can also calculate it with this equation too. P equals VI, power equals voltage, PD, times current. Moreover, if we substitute Ohm's law into this, we swap the V for IR, and we end up with the alternative equation, P equals I times R, or P equals I squared R. The electricity that comes out of a battery is DC, or direct current. That's current that only flows in one direction. AQA these days have an obsession with calling it direct PD, which is pointless but means the same thing. Direct PD is a potential difference that is only in one direction, and this results in direct current. Mains electricity that comes out of your socket is AC, alternating current, resulting from an alternating PD. In the circuits in your home, the neutral wire stays at a potential of 0 volts, while the live wire, well, its potential varies, but it averages out to an equivalent of 230 volts. So we say this is mains voltage or mains PD. This alternating PD causes current to go back and forth at a frequency of 50 Hz, 50 times a second. If you hooked up a battery and mains electricity to an oscilloscope, we'd see these two traces to see how the PD changes over time, or doesn't change in the case of DC. Of course. In a socket, the wire with blue insulation around it is the neutral wire, while brown is the live wire. The third yellow and green wire is the earth wire, and that's connected to the pin at the top. It's not necessary to complete the circuit, and there should be no current flowing through it normally. It's a safety wire that's connected to the outside of metal appliances like kettles or toasters. So if anything goes wrong with the other wires inside of the kettle, current will flow through it to the ground instead of through a person if they touch it, which would give them an electric shock. Also in a plug, a fuse is attached to the live wire, which is designed to melt or blow if the current exceeds a certain number of amps, usually 3, 5 or 13 amps. If something goes wrong in an appliance, the current may well spike, so the fuse will blow before too much damage can be done to it or the user. You may need to use P equals VI to calculate the normal operating current for an appliance to deduce what fuse should be used in the plug. Let's say that a microwave draws 800 watts of power from the mains. What fuse would it need? Well, we know power is 800 watts. We know PD or voltage is 230 volts because it's mains. So we use P equals IV to find the current and rearrange it. Current is equal to P divided by V. So that's 800 divided by 230. That gives us 3.5 amps. We can't use a 3 amp fuse, otherwise it would just blow under normal operation. So we go for the next one up, a 5 amp fuse. A 13 amp fuse would work as well, but the current would have to increase to that before it blows, and that could be more dangerous. Electricity is supplied to homes and businesses by the national grid, a network of power stations, cables and more that transmit it across the country. The current produced by a power station is quite large, so much so that if it went straight into the overhead cables you see above you when you're out and about, a huge amount of energy would be lost as heat due to the resistance of the cables. To reduce this energy lost, transformers are used. Triple people, you'll need to know exactly how they work for paper too, but for now we all just need to know what they achieve. A step-up transformer outside the power station increases the transmission voltage to over 100,000 volts. As P equals VI and power stays roughly the same in this process, if PD goes up, current must decrease as a result. This decrease in current means less energy and power is lost due to heating, and we can see this from the other power equation, P equals I squared R. Lower the I, lower the P lost. Of course, having such a high voltage going into homes would be dangerous and unnecessary, so we have a step-down transformer nearby to reduce it down back to a more safe 230 volts. Next, or the particle model of matter. Density tells you how compact mass is for a material or object. For example, a cup of iron has a much higher mass than a cup of cream, showing that iron has a higher density. But we don't measure density in kilograms per cup, but kilograms per meter cubed. So the equation is this: density is equal to mass divided by volume. The symbol we use for density is the Greek letter rho. It's just a P without the ear on it. Density is dependent on what particles make up the object and also how tightly packed together they are. We know water vapor is less dense than liquid water because even though both made from water molecules, they're more spread out when a gas, so there are fewer of them in every meter cubed. Finding the density of a regular object, that is an object with a volume that can be calculated using its dimensions, is easy. For example, the volume of a cuboid, a rectangular object, can be calculated by multiplying the length of its three sides, and then we just pop it on a balance to get its mass and then use the equation to find the density. For dimensions that are a few millimeters in length, a ruler won't be that accurate, as its resolution will likely just be 1 millimeter. So you could use vernier calipers instead. They usually have a resolution of 0.1 millimeters, a tenth of a millimeter. Objects that are very, very thin, like wires, need a micrometer instead. They usually have a resolution of 0.01 millimeters or a hundredth of a millimeter. The volume of an irregular object, like a chess piece for example, cannot be calculated from measurements. Instead, we use a displacement can, also called a eureka can, after the Greek philosopher Archimedes got into a bath full to the brim, displacing the same volume of water as his volume. Tie thin string around the object and gently lower it until it's just under the waterline and wait for the water to stop dripping out into the beaker that you hopefully put there beforehand. We decant this water collected into a measuring cylinder to get the volume of water displaced and therefore the volume of the object. Solid, liquid and gas are the three main states of matter. For example, water can be ice, a solid, where the particles vibrate around fixed positions. It can also be water, where the molecules are still touching but free to move past each other, and gas, water vapor, where the particles are far apart and moving randomly, which is why it can be compressed, while solids and liquids cannot. To melt a solid or evaporate a liquid, you must supply energy, usually in the form of heat, to overcome the electrostatic forces of attraction between the particles. If you have a block of ice and supply heat to it, its temperature will increase. The particles vibrate faster, which means they gain in kinetic energy. However, once it reaches the melting point of 0 degrees C, its temperature will remain constant until it's all melted. Only then will its temperature start increasing again. The same thing happens when it reaches 100 degrees and it turns into a gas. But why the constant temperature? After all, energy is still going into the ice, but during a change of state, the particles don't gain kinetic energy, but rather potential energy. We say that any substance has internal energy. That's the sum of the kinetic energy and potential energy of all particles in a substance. You need to know this definition. Only one of these can change at a time. An increase in temperature means we must have an increase in kinetic energy of the particles, while a change in state, when heating anyway, must mean an increase in potential energy. We have equations for both of these energy changes. We saw at the start the equation for increase in thermal energy, which was E equals mc delta T, mass times SHC times change in temperature. We now know that this is only for an increase in kinetic energy of particles in a substance when there's a change in temperature. During a change of state, the temperature stays constant, so we can't use the specific heat capacity equation. Instead, we use the SLH equation, specific latent heat. SLH of a substance tells you how much energy is needed to change the state of 1 kilogram of it. For example, the SLH of fusion, that just means melting or freezing, for water to ice is 334,000 joules per kilogram. That means the equation for energy needed to change state is this: E equals ml. Energy equals mass in kilograms times specific latent heat in joules per kilogram. We know gases consist of particles that are far apart, moving fast and randomly. If you heat the gas, the particles gain kinetic energy and they move faster. This means that they collide with the walls of the container the gas is in with a greater force and more frequently, which results in an increased pressure, pushing outwards. And that's it. Hopefully this has been useful. Leave a like if it has, and leave any comments or questions you have below. And hey, come back here after the exam to let us all know how you got on. We'd love to know. Click on the card to go to the playlist for all 6 papers, and I'll see you next time. Best of luck.